Welcome. Well, thank you for coming out today. My name is Fred Dushin. I'm going to talk about how we have integrated Solr into Riak, which is a NoSQL database. I'll talk a little bit about that today. So just by way of introduction, I'm an employee at Basho Technologies. I'm relatively new at Basho. I come from a long pedigree of abandoned technologies going all the way back to Corba. Web services had its heyday, and message-oriented middleware, things like RabbitMQ, SonicMQ, different message queuing technologies. I joined Basho because I was really interested in distributed systems, and I really appreciated the way Basho takes on the problem of distributed data, consistency, and recovery in the presence of failure. And I really haven't been disappointed at all in coming to Basho. It's fascinating work, and I think in some ways we're sort of in the golden age of distributed systems. We're learning so much with so many different approaches, with the approach that Basho takes, that Riak takes with sort of Amazon-based systems, the Solr cloud approach with Zookeeper and leader election and all the stuff that's going on in Hadoop. It's really a fascinating time to be involved in this. I'm on GitHub. I'm not a big user of Twitter, so I have an email account that people can reach out to me. Now, I'm also into soccer and vintage Land Rovers, but I'm not going to talk about that today. Unfortunately, we could talk about that later. What I do want to talk about, though, is how is it even possible to query a distributed NoSQL database like Riak when you have data that's replicated in many different places? How do you get correct results out of that? And I'll talk a little bit about how Riak does that. Okay? What's more interesting and what excites me about the way we approach things with Riak and at Basho is what happens when things break? What happens when you lose data on a node? How do you recover from that? How do you detect it, and what do you do? Okay, so we'll talk about that. Now, in order to do that, I actually have to set the stage, so I have to talk about how Riak distributes data, okay? And I have to talk about how Riak repairs divergence when things go wrong, and how it detects them. And in order to do that, I have to talk about what Riak is and what Riak search is. Okay? And what I hope to conclude, if things go well, if I make it on time, I want to be able to define what Solr brings to Riak. That should be pretty obvious, but also what Riak brings to Solr, because you have lots of options as Solr users for using distributed, for distributing your indexes and your data over a cluster. Riak is another option. Maybe not be the right option for your use case, but it is an option. Okay, so what's Riak? Well, it's a distributed key value store. So there are two pieces there. Key value, okay? Very simple set of operations. Put, create, update, delete. Create, update, delete. And read, of course. It's distributed in the sense that it runs on a cluster. Now, for development purposes, you can run Riak on a single node. You can even run a cluster on your laptop, like we usually do. But in a real deployment, Riak is going to run inside of a LAN on multiple machines, right? That's where you get replication and redundancy and high availability. Riak is based on the Amazon Dynamo model. A paper was published a number of years ago, and Riak is a faithful implementation of that blueprint. And in that model, for that use case, there is a prioritization of availability over consistency of data. Okay, so the system will generally, in the presence of some failures, be available for both read and write operations, okay, even if parts of the system aren't running. Okay, when the system comes back up, or when the parts of the system come back up, there are processes, which I'll talk about, which heal the data that was missing, it wasn't written to. What that means is there may be cases where you have inconsistency in your data. Okay, and Riak has a number of solutions for resolving those inconsistencies. I won't be able to go into details about that because you guys are here because you're interested in search. Okay, Basho and I are here at the booth. We can talk. We can answer any interesting question or any questions you have about some of the more subtle details. And I'm going to be glossing over some of the low-level details just to give you a picture of how the system works. Now, another thing that Riak provides is what I've characterized, what I call elasticity. We sometimes call it operational simplicity, but the idea is that if you have a cluster, you can grow that cluster while the system is running. You don't have to take down the cluster, reorganize it. You can add a node. Data gets automatically distributed. Okay. So I want to provide a little bit of a glossary, a couple of terms. I said Riak is a key value store. A key is just any sequence of bytes. A value is just an opaque blob of data. Again, another sequence of bytes that are stored. We have other concepts in Riak for organizing keys into namespaces. So we have a bucket, where you put a key in a bucket. But buckets and bucket types, which are essentially namespaces for buckets, have other features that allow you to assign different properties to all of the keys in that bucket. So for example, a replication factor you can apply to the bucket. So any key that's put into that bucket has that replication factor, or it uses that backend. Okay, so it's kind of a namespace, but it's also a container for properties or policies for how you write that data. And we'll see one of those properties is whether you index it or not and how you index it. Whoops. Okay, I'm sorry. The picture was there. I'll just talk to it. I'll use the term BeKey to refer to a bucket and a key together and a bucket type, but I'm going to gloss over bucket types. Just pretend they're there or pretend there's some sort of global bucket type. A BeKey gets mapped into a value in Riak. Okay. So suppose you have all of these BeKeys out there, right? Maybe, let's say it's a finite number of BeKeys, buckets and keys, but you could imagine it being infinite as well. So Riak has a way, and we desire a way to distribute those keys evenly throughout a cluster, okay? And we have the concept of a ring of data whereby we take a BeKey and we compute its SHA-1 hash, right? So a SHA-1 hash, as you probably know, is a one-way function which will take an arbitrary input and generate a 20-byte sequence of data. And if you read Applied Cryptography, Bruce Schneier's book, there are interesting properties about that function, namely to avoid collisions as much as possible. So 20 bytes is really a monstrous number, right? It's somewhere between 0 and 2 to the 160 minus 1. Okay? And 2 to the 160 that's the big number. That's a pretty big number. So by taking the SHA, what we can do is we can partition that data into, I won't call them buckets, I'll just call them partitions. Okay? So in other words, if the SHA of a particular key falls between the range 0 and that big number that follows the 2, it goes into segment 1 or partition 1. Okay? Now SHA will give us an even distribution, relatively in the limit. It'll give us an even distribution. So generally what we're doing is trying to evenly distribute the data around what we call the ring. Now in Riak, a ring is generally a well-defined size. I'm using 8 in this case because it's easy to talk to, it's easy to envision. I can draw pretty pictures with 8 of them in it. by default, Riak ships with a ring size of 64. So bear that in mind. Usually you're looking at 64 in a real, 64 partitions. Okay, so how are partitions distributed around a cluster? Well, I may have mentioned, I forget, a Riak cluster is a set of homogeneous nodes, to the extent possible, that are connected together in a generally in a local network. I've color-coded each rung in the ring, as it were, each partition, with the node ID. So generally what we will do is we'll assign partition 1 to node 1, partition 2 to node 2, 3 to node 3, and so forth until we exhaust all of the nodes, node 5, and then we wrap around and we keep partitioning. We keep moving those, or we assign the partitions to those nodes. Okay? Makes sense. The result of that is what we call a cluster. Okay. A Riak cluster is a collection of nodes with partitions roughly evenly distributed around, and where each partition contains keys, which themselves are evenly distributed. Okay, so how are entries replicated? Well, suppose we have a BeKey and it gets mapped to node 6 under its SHA, goes into node 6. Each bucket has a replication factor, what we call an n-val, and that will get replicated to the next succeeding partitions in the ring, right? And given the assignment, right, those will go to the purple node, the green node, and the yellow node. So they'll get replicated over 3 nodes. I have an interesting story about replication, but unfortunately I think time is going to prohibit me from telling you about my experience taking a flight from Boston. We lost hydraulics, right? But we had a replication factor of 2 or of 3 in the hydraulic system, so that was a good thing. We were able to fly back to JFK. Okay. We call the node that it gets mapped to under the SHA the responsible partitions, and these subsequent partitions, they get replicated to primary partitions. It will turn out that there are fallback partitions I'll just allude to very quickly. So I'm going to illustrate very quickly what happens in a put scenario, because I want to be able to tell you how replication works, so that you're sort of lined up for understanding how data is replicated in Solr. Well, it's actually quite simple, right? The data will get written to node 6, and then replicated to nodes to partition 6 on node 1, and replicated to 7 and 8. Once we get a quorum of results back, we'll return an OK, on a put. What's more interesting, though, is what happens in the case where a node is down or the network is segmented. So the preferred node, right, the preferred partition is not available. Well, we have what's called a quorum on writes, right? Or we have a write value. This is another parameter in Riak. And by default, we assign that variable to be the atom quorum, which means essentially at least, it's essentially majority rules. Okay, so we wrote the two, we updated our value, our key agent with a new value. I'll come back to what those values look like when we talk about Solr. Node 7 was not available. We have, though, another node in another partition in the ring on the cluster. cluster which is available. So what Riak will actually do is write as that node as a fallback, write to that partition on that node as a fallback. When the node comes back up, it will return OK. When the node comes back up, that data will be moved back to its target node. This is what we call hinted handoff. We have a number of handoff patterns that we provide in Riak, and we can talk about those. I'm not going to go into great detail about this. But this should give you a sense of how the system is available for writes, even though part of the system is down. OK. I'm going to illustrate one more concept in Riak, which is called read repair. OK. Let's imagine that node 2 goes down and we lose the disk. Okay, so the data that was supposed to be on node 2 in partition 7 goes away, and it comes back up. If we do a get, by the way, this is Python code I'm illustrating on the client side. This is a client outside of the cluster. We have libraries for Python, Java, PHP. I'm just using Python because it's nice and succinct. We also have HTTP, which I'll show you later. If I do a get, right, my read value is set to quorum. So all I need is a majority, 2 out of 3 in this particular case. And I have them available, right? If I go to node 2, it's going to ask for that data, and it's not found. Well, there's a feature in Riak where when you do a read, right, it will then, after it returns the result to the user, it'll actually asynchronously try to repair the data that should have been on that particular node. It's almost like sort of, you could think of it as Schrodinger's cat, right? You don't see the data repaired until you actually observe it. Okay. Why is read repair interesting? Well, because of a feature in Riak called anti-entropy. So when we write data into Riak, we're actually, one of the things we're doing as we do the writes, or actually asynchronously as we do the writes, is we're recording the BeKey together with the object hash. Okay, what the data should be under a different hash algorithm, not SHA-1, just what the fingerprint of that particular KB datum is. And each node keeps track of these hash trees. So the trees are organized into segments, okay, with essentially bucketed up keys and hashes. And then each of those lists, or each of those segments, are themselves hashed, okay? And those form a sequence of segments which themselves are hashed, and so forth, all the way up to a root node. So why would we do something that complex? Well, a nice feature of this is in a stable system, when everything is as expected, you can do a unit time comparison between two trees. All you need to do is look at the root node. If they're the same, then all of the data is the same. Okay? And that's exactly what we do, right? So we maintain hash trees on each of the nodes, and it's a little bit more complicated, a little bit more subtle. We actually maintain sets of hash trees. I won't go too much into the details. I think I'll at least leave you with a bullet that describes what we're doing. And if we find divergence, symbolized by these different colors, right? So the blue and the orange are different. Oh, which subtree is different? Oh, the green and the yellow, and then which segment is different? Oh, we have a value on node 3, which should be on node 2. What do? We trigger a read repair, okay? And the read repair will fix up the data. So AAE is an asynchronous process. It's running all of the time, right? And it's looking to detect divergence in replicas, okay? And if it finds divergence, it'll repair that divergence. There are some other interesting details. The hash trees are stored on disk, so they don't consume memory. If you've got billions of keys, right, in your key space, you're not ballooning memory with all of that hash tree data. There's asynchronous updates with back pressure, all kinds of interesting stuff, right? The details or the implementation is always more subtle and complex than this high-level description. Okay. Thank you for bearing with me. I needed to set the stage for Riak so that you understand how data is distributed, right? How Riak endures read and write availability in the presence of failure, right? In the presence of failure of one of the nodes, maybe there's a disk has gone bad, a power supply has gone, you name it. And how Riak actively tries to repair entropy, right, or a divergence in the data. Okay, so what's Yokozuna? This is why you're here, okay? So Yokozuna is an extension of Riak, which provides search capability over values stored in Riak. So remember, Riak is KV, okay? It's a key value store. And in general, in Riak, absent or independently of Yokozuna, values are opaque. Riak never looks at the value. It just stores it as a blob. Well, now with Yokozuna, you can extract data out of that and store it in Solr. Okay, so I'll talk a little bit about how data is indexed, and I'll talk about how data is queried through, essentially through legacy distributed Solr. So in case you're wondering, we're not using Solr Cloud. Okay, we're using distributed Solr as provided by the runtime, by the libraries. We're using shard parameters and so forth. I'll describe that. And by the way, this is all open source, so it's on GitHub, as is most of Riak. There's a commercial extension to Riak, which I won't go into. But for the most part, everything that I'm talking about is on GitHub. Okay, so Yokozuna is an application in the sense of it's a component that runs inside of Riak. And it provides all kinds of nifty features, administrative query APIs, and so forth. And it has capabilities for data extraction, JSON, XML, and so forth. I'm not going to go into detail of that. With that, please come talk to us at the booth if you have questions. But what I really want to focus on is indexing, query, and active anti-entropy in Yokozuna. By the way, there is a monitor as well between Yokozuna and Solr. The purpose of that is to keep Solr running. So if you look at a cluster with Yokozuna enabled, what we actually have are running instances of Solr alongside each instance of Riak. Okay? So for every Riak node, there's a corresponding instance of Solr. If Solr goes down, Yokozuna will reboot it. If Yokozuna goes down, or if Riak goes down, we have some code that runs inside of Solr, which will actually take Solr down. So it's always one-to-one on a particular node. So it's a separate JVM. I didn't mention Riak is actually implemented in Erlang. It's not implemented in Java, so it's a separate VM, a separate OS process. So we communicate over pipes, and we make that work. Okay, so in order to write any data into Solr, we need an index, a Solr core. Okay, and what we do is we provide administrative operations either through our client libraries or through HTTP for creating a search index, which is really synonymous with a Solr core. So if you invoke this command, that index will actually get created on every node in the cluster, on every Solr node. Okay, and that's done we have a gossip protocol. We can manage all of the communication internally through a component in Riak called Riak Core, a whole nother level, a whole nother topic, which we definitely won't get into. But that is the mechanism by which we go out to each Solr node and tell it to create an index. I mentioned bucket properties. I mentioned buckets before and properties associated with them. So one of the, in order to use a, in order to index any data that you write into Riak, you have to associate a search index, my index, right? Or you have to associate a Solr core with that bucket. Because you might have other buckets that you don't want to index data, right? So you can turn on, you can adjust the granularity in Riak by which you index data. Okay, and then you can store data, right? You can do a normal write in Riak, right? And when that data is replicated in the normal Riak way, it will get indexed and stored in Solr. Okay, so any write into Riak with a sufficiently configured bucket will result in indexing in Solr. Okay, makes sense. Correspondingly with deletes, right? You can delete data in Riak, and it'll get deleted in Solr. Now, what we don't support is contacting the Solr node directly and doing a write. So if you want to write, read or update data, you have to do it through through Riak, either through the HTTP API or through some of the client libraries. Later, please. Okay. So I'm going to skip over some of the schema here, but just to give you a sense of the use case, we provide a default schema. You can extend it. You have to include these fields. We provide a unique field that is used for identification. You can also get, oops, sorry, wrong way. You can also get the bucket, the type, and the key out of Solr. Okay. These parts of the schema are internal bookkeeping. I'll come back to those in a second. So now, query. All Solr queries are made on the Riak endpoint. Okay, so technically, yes, you can reach out to Solr directly and run a query, but I'm going to explain why that won't work. This is sort of the why is this interesting kind of question. How is it even possible to do query? Well, the answer is you have to go through Riak because we do some magic under the covers. As I mentioned, we used legacy distributed Solr to route queries using shard parameters to the appropriate nodes. Solr does all the aggregation and returns the result through Riak. So Riak generally does, thank you, the Riak doesn't interpret the results or get in the way of the results at all. Okay, so it's anything that you can do, right, with distributed Solr, you can do through Riak, both on the query side, right, for what's the query and what are the results. There are some footnotes. We can talk about those at the booth. Okay, so what's the magic? How does this actually work? Well, if you think about a query, right, we're asking, where is all of the data that I'm interested in, right? Well, how does Riak know where that data is if we're running the query, right? If we're not providing keys. All Riak knows is key value, how to look up something by key and value. But one of the things Riak Core can do is it can compute covariance sets. So for replica sets 6, 7, and 8, if it looks on 8, it will get exactly one of those replicas. Similarly, for 3, 4, and 5, it can look on 5, and for replica sets 1, 2, and 3, it can look on node 3. Okay? So a covariance set is a subset of all the partitions in the set of partitions, right, in the ring, such that for any key, any B key in the key space, there's exactly one partition you can reach. Okay? Those aren't unique. And in fact, Riak will compute those regularly. Okay? So that, well, actually, let me just show you. I'll explain why. Right? If we run a query, right, we have an API for that, or you can do it through HTTP. That will go to Solr, but because the covering sets are on node 3 and 5, we only have to go to node 3 and 5 to make that query. Now, there's a little bit more of a subtlety here because indices are not per partition, they're per node. So we have to actually add some extra filtering. So here we have a shards parameter which tells distributed Solr to go to node 3 and node 5. When it gets to node 3, it will add this filter query to the query to only look at partition data, only search over data on partitions 3 or 8. Okay? And similarly on node 5, there's a little bit of a detail there to make sure that you don't have any overlap using the responsible partitions. I won't go into the detail there. So the shard translator, that's a component that does the translation. I want to have that there in case anyone says, what's that weird node 5 parameter? I don't recognize that. Well, that's what we use to do the translation. Okay, very quickly. I talked about AAE. Let's imagine that we just lost data on Solr, okay, on node 2, right? So we had some, sorry, that's supposed to be dimmed, but it doesn't show up on the screen. Sorry, we had some index data on node 2 in Solr, but let's say for the sake of argument, we lost the disk. Well, we have another feature in Yokozuna called Yokozuna active-active entropy, which maintains hash trees between the data on Riak and the data in Solr. So if it's missing, we'll do the same algorithm for walking down the hash tree to find divergence. And if it's missing, we'll write it into Solr. Conversely, if the data is missing from Solr, or if the data is on Solr but not in KV, we'll remove it from Solr. So KV, Riak, becomes canonical. Okay? It becomes the data store for your data, and Solr is the indexing store. Now that you can write your own schema and store data in Solr as well, but the master record is in Riak. Okay, very, very quickly, I want to talk about the entropy data field because I apologize. Because I want to be able to talk about a bug that I'm trying to fix or an enhancement. Thank you. So the YZ entropy data field is a field in the schema that has to be there, but note that the data is indexed and not stored. So a YZ ED entropy data field typically looks like this, right? It's a string that contains the bucket type, the name, the key, the partition, and the hash. And we have an API internally that we use, which will iterate over those entropy data fields and yield a result. Yield all of the data in that entropy data field. Now remember what I said, it was indexed but not stored. How does that work? How am I getting data out of something that's indexed but not stored? Well, it turns out that those YZED fields are essentially unique, right? So we can iterate over Lucene terms, right, that are not stored, they're just indexed, and we can get the data out. So one of the things I'm looking at now is trying to improve that a little bit by using cursor marks and deep paging. Anyone has any experience with that? I'd love to talk. Please reach me out in the booth. And this is the component that we ship with Jetty, that ship with Solr that does that, entropy data iteration over the terms. I just wanted to very quickly say what we're doing. The improvements to entropy data traversal is something that I'm working on now. That's in GitHub. We have a big set of changes on batching and asynchronous indexing to improve the performance of index throughput, and we're moving up to Solr 4.10. Okay? And there's some other future work we're talking about doing, particularly around reindexing data on schema change. We have a mechanism for do that. Just delete the data, and AE will take care of it for you. Okay. So what does Solr bring to Riak? Search, obviously, right? For Riak customers who want to be able to search over their data, Solr does the job for us. What we bring to Solr is a way of doing distributed Solr, right, which is effectively transparent. We've effectively embedded Solr inside of Riak, so you don't have to do any of the management of Solr. It's transparent. You can write and read your data like Riak, but you can query it using all of the Solr Lucene syntax available through Solr. And we provide high availability and all kinds of other nifty features with Riak. Okay, so 3 minutes. Sorry, you asked first. Or, sorry, you did. Yeah.
There's a couple of slides before where you're putting the Solr index in a particular node. Was it intentional to show the same index in multiple nodes? Or should it have been index, my index, shard 1, or partition 1, my index, partition 2?
Okay, so the question was, just for the studio audience, do we have an index per partition? And the answer to that is no, we don't. We actually have one index, which is shared by all of the partitions. That's why in the query, right, we had to add those filter query parameters when we go to that node to say, only look on these partitions.
So they're logically separated by a separate field, which is the
Correct.
partition name.
Exactly, yep. Yes?
So when you have two engines really storing and working with your data,
Yeah.
how do you deal with the problem of data being duplicated? Does Solr also store all the data sets? Or when you return data back from a Solr query, is that returned purely from Solr, or does React or SQL store?
Okay, good question. So the question was, is the data, to what extent is the data replicated in Solr? And when you query Riak to get to Solr, do you go back to Riak to get any data? The answer to the latter question is no, we don't go back to Riak. We only go to Solr, okay? And you are free to write your own schema for Riak to store data, but a common pattern, and not an unreasonable pattern, is to just use Solr for the indexing, right? And return the bucket and the key so that you can later do a lookup in Riak to get the actual data.
But that's after that. It's
Yeah.
not part of a single query to the engine. For example,
Yes, that's correct. Correct.
End user still knows it's React answer.
Correct. That's true. So if you wanted to do it in one shot, if you wanted to query and get the data out at the same time, what you would need to do is store those fields inside of Solr as well. So you would have data replication in that case.
Would you like to do that in React? Or why wouldn't you do that in React? You can have this tool.
Yeah, we could do it in Riak. We definitely could do it that way, maybe as a specialized API, right? Give me the data such that this parameter is true. Okay. I'm sorry, I was asked, I apologize for not being able to address your questions, but I can do it outside of the hall. Okay, thank you very much.